Srikant-Fuchs equation in that case for this Grassmannian variety is given by this toric data.
Right. So the f could be mapped to actually a period integral expressed as a path integral using the 𝗰𝗵𝗶𝗶 description. So it could be a beautiful map. Okay. Thanks.
Yeah.
Okay. Thank you. So. Let's thanks, Koushik. If you could unshare. Thank you. Let's move on to the next talk. It's Arnab Rudra.
Yeah, I have to unshare, right? Somehow.
Yeah.
Let me try to share. Am I visible?
Yes.
Yeah.
Okay. We are very happy to have Arnab Rudra from 𝗰𝗵𝗶𝗶, and today is going to tell us about massive higher spin amplitudes in flat space. I will give you a notice when you are about 20 minutes.
That would be great. Thank you. Thank you for giving me this opportunity, and thank you for this wonderful conference. Today I'll be telling you about some very simple computation that we have been doing regarding massive high spin amplitudes in flat space. I'll try to give a general introduction to the problem, and then I'll present a very simple case. But the most general computations that we have done are very long to present in the slides, so I will request you to look at our papers. So this has been done in collaboration with two of ISO students, Mahesh and Raj, and I can't think of solving this problem without them. And what happened? And we reported this in this archive article, which has recently appeared in JHIP. Okay, so before I go into the motivation, let me try to define the problem, that what problem we tried to solve. So I told you I will be talking about high spin amplitude. So let me define what is high spin. So we have been hearing a lot of talk here on flat space holography and all this, but so one part of that is that in flat space, the symmetry group consists of translation, rotation, and boost, and all this together is known as the Poincare group. And a definition of a quantum particle is simply an irreducible representation of the Poincare group. Okay, then from the representation theory, it follows that quantum particles are uniquely determined by the Casimirs of the Poincare group, which are known as the mass and the spins. So in 3+1, there is only one spin, but in higher dimension, there will be more spins depending on the number of Casimirs. Okay. So in general, in n+1 dimension, the number of spins is basically the floor function of n/2. So in the literature, for some reason, any particle that has spin more than 2 is known as a high spin particle. So whenever I refer to high spin in this slide, I mean any particle which has spin more than 2. And in 60s, Weinberg, and later there is a work also by Weinberg and Witten, which basically showed that higher spin particles cannot be massless. So they're necessarily massive. And I believe that's one of the reasons that though this problem is simple enough, were not studied in foundational days of quantum field theory. Okay, so my goal, having set up this terminologies, my goal is to give you a closed form expression of tree-level amplitudes with arbitrary massive spin J exchange. So if I can use a Feynman diagram, then what we are trying to do is that we are looking for tree-level diagram. At this point, only 4-point functions, though I believe this can be generalized to higher point functions. With massless external legs, again, this can be done with massive external legs, but massless external leg is basically the motivation. When I'll talk about the motivation part, you will see it coming from all sorts of very exciting work. Some of them are India and some of them from outside India. So we are looking for a 4-point function where these legs are massless, external legs are massless, and this exchange particle is an arbitrary massive spin J particle. If they are scalar, the expression is very simple and easily available. We are trying to do when the external legs are spinning. Okay, so that's the question that we had tried to address. So once I have defined our question, let me try to give a very brief motivation that why we are looking into this problem. And again, as I said, that this is, I only mentioned work of few, but there are many exciting work going at this point. And if you can mention that this work is in directly connection with some of the exciting things that people in the IFR are doing. So let me elaborate on that. There can be many motivations, but for me, the motivation is roughly coming from understanding what Suman mentioned about the CRG conjectures, theories of gravity. So last year, Penrose got the Nobel Prize, and we know that the important work of Hawking-Penrose singularity theorem, which basically says that the classical dynamics of gravity from a generic data, not from a very specific data, typically produce singularity, right? Though the singularity is inside an event horizon, but it produces a singular configuration, which basically says that even gravity as a classical theory is singular. So then, as all of us have learned in past, that whenever we have come across any classical singularity, we hope that quantization will save us. But in case of this, if we just take Einstein-Hilbert and naively quantize, I mention it naive quantization because maybe we have to be more smart in doing the quantization. But if we just do naive quantization of gravity, it doesn't help. It rather comes with more severe problem of non-renormalizability and all sorts of issues. Okay, so then the lore was that maybe higher derivative corrections can help us, because higher derivative corrections will not save us, will not change the nature of gravity at long distances, but it will change the dynamics at short distances. So maybe it will resolve the singularities. Okay, but as all of you who had at least 2 courses in QFT knows, that any form of higher derivative correction always comes with a new scale because they come with derivatives. So in my mind, at least there are 2 kinds of scenario that can appear. That the new length scale is the scale that is the Planck scale. It can well be true that all the high derivative corrections become important at the scale where the quantum gravity corrections are important. And in that context, whatever I am saying is not important, because I am assuming that there exists a length scale which is parametrically larger than the Planck scale. So for this talk, this is more or less an assumption. And also I am not aware of any work which has tried to prove that the scenario must be 2, not the 1. But if there is, and I don't know, please let me know. But I can just point out one analogy with the standard model, that in the 40s, there was this beautiful theory of Fermi theory of beta decay, which people turn out to be not unitary. It violates unitarity at some scale at 300 GeV. So that's roughly the scale that I think like the quantum gravity scale in analogy. And then when people tried to, people found standard model, people found that the new corrections kick in at 80 GeV, roughly 83 GeV, the mass of the W boson. So it always happens. In that case, there is an example, not in a non-gravitational theory, where the corrections kick in at a scale which is parametrically smaller than the scale where I expect the unitarity to break down. And there is this beautiful work of Satish Joglekar and other people who try to approach this problem in an amplitude way, and try to argue that how I can come up with a theory which is unitary at all scales, and it gives a Fermi theory of beta decay at low energy. And it basically shows that there are 2 possible choices, and one of them is the standard model that Glashow, Weinberg, and Salam got it. So our motivation is to do something similar in presence of gravity, though I must say we are very, very far from that. Okay, so in this direction, so I mentioned that a high derivative correction, and all of you are aware of this beautiful paper by these 4 gentlemen, Camino, Maldacena, Edelstein, Zubedov, who basically showed that high derivative corrections to gravity necessarily implies massive higher spin particles, and vice versa actually. So so that is their conclusion, and they and among many things they showed in that paper, which I not try to review because I think most of you know about that. But as all of you know, that this is not sufficient. This is a necessary condition that we should have massive high spin particle, but this is not sufficient because really to have a good theory with all causality at all scales, we should have some form of restrictions on the 3-point functions and maybe on the spectrums. Okay, and for that, I believe we need the explicit expression for the 4-point functions. Okay, so in this direction, I mentioned this work by the KIFR group, where they tried to compute this most general 3-point function in various dimensions for 2 gravitons going to 1 massive spin particle or 2 photons going to 1 massive spin particle. And that's basically you can take as our starting point for this work. Okay, so if 3-point functions are available, then what's basically the difficulty in computing the 4-point function? Because usually it's a very straightforward exercise. And actually, I must say it is a straightforward but algebraically intense exercise. And this algebraic complexity, naive algebraic complexity, comes from the fact that the propagator for the spin J particle is a mess. It's hugely complicated. So it has this. I just flashed one transparency. And because of this big expression of the propagator, the computation looks hard at the first glance. Okay, it comes from the complexity of the expression of the propagator. So, so with that thing in my mind, with that thing in our mind, we thought of taking the 3-point function and tried to approach this problem brute force. Okay. So before I go into again the explicit computation, let me just set up some more terminologies, which is, I believe, more general for structure of the spinning amplitudes. And so the most general structure of a spinning amplitude roughly takes this form, where I mentioned 2 things. One I call Ti, which is a function of polarization and the momentum. And this is a function of only the only the momentous. Okay. So this separation is usually called the tensor factors, and these are called the form factors. Okay, so for 4 scalar amplitude, this is just naively 1, and this is the full of the amplitude. Okay, but in case of spinning amplitude, there is more structure in it, and this index I is basically sum over all Lorentz invariant independent structures. Okay, so the sum over I depends on which amplitude we are interested in. And we'll see some of the expressions later. Okay, so as I said, that these F's are called the form factors and Ti's are called the tensor factors, and we have to basically do the sum over all possible independent structure. But since I mentioned to you that I'll be mostly interested in massless particle, the basis we will always be choosing for this is a gauge invariant basis. Okay, for more general particle, the basis is much higher dimensional than for the massless particles. Okay, so with that thought, I just want to mention one more result. Again, it's available in the literature, and this provides an important cross check for us that what the computation we did brute force is correct. And the cross check is the following. It's only available to my knowledge in 3+1 dimensions, though there is no reason to not do it in higher dimensions as well. And it comes from the fact that massless particles in 3+1 dimensions are basically given by one quantum number. It's called the helicity. Okay, now consider a configuration where the 2 incoming particles are coming along the z-axis, one coming along positive z-axis, one coming along negative z-axis. And since it's a 4-point scattering, I can always map it to a xz plane or any 2 plane. I choose it to be xz plane. And let's say the outgoing particles are in the xz plane and at an angle theta with respect to the incoming particles. And let's say the 4 particles have helicity h1, h2, h3, and h4. Then using very simple methods, you can show it that in the center of mass frame, the expression for the tree level amplitude takes this form. Okay, this constant is fixed. I have not given it in because of the space. It's available in our paper. It's explicitly known. The power of S is explicitly known. This is the pole part. There is a S power J factor, and this is the Wigner matrix, that we have all studied in our quantum mechanics course. And the two arguments H and H prime are basically the difference of helicities. Is H1 minus H2, H prime is H3 minus H4, and J is the J of the exchange, the spin J exchange we are talking about. Okay.
Oh,
so
one question, sorry to interrupt. So this form is only for tree level or all loop levels?
This is so if I go higher loops, then this pole structure is no more true. This will be more.
Okay,
this will be replaced by a more general function with all sorts of branch cuts and other things. But the angular dependence, I believe, is true in general.
Okay, and this n tilde will normalization will also change, right?
Normalization, the way we determined it, it's explicitly we have done using representation theory for tree level amplitudes.
Okay.
Probably it's possible to do. See, you can always shift the sum of the normalization to the analytic, the function on S, right?
Okay.
Here the function of S is also very explicit, so all the numbers has a meaning. So in general, I don't know, in loops, depending on how you normalize the log function and everything, maybe this function can be determined. I have not tried that.
Okay. Thank you.
So this is an important cross check that we will be doing whenever we compute this amplitude. That will go to center of mass frame. We put the expression of the helicities and we see that whether we get these expressions correct, whether we get these angular distributions or not. Okay. So now let me mention the method we adopted. I believe this method is known in CFT, and I will demonstrate it only for the photons, because the case of gravitons is just double copy version of the photon. So and we did it in the paper, but for sake of explanation, we restrict to the photon for simplicity. Okay. So before I go ahead, let me say some few words about the 3-point function, and some part of it has been done by the TIFR group. So there are in the paper we define basically two types of dot products. One is this dot product with respect to the eta, which is a space-time metric, and second dot product is with respect to the theta, which, if you remember, I used to define the propagator. So theta is this one. Okay, so theta is basically the metric which is plane transverse to the particle. So theta is a metric in that. Okay, so it's related to eta, but it's not.
Just to get my bearings right, you're trying to derive that the expression that you just showed. Just go back to the slide that you just showed.
No. You will see. I am not trying to say, because this expression is only correct in the center of mass frame, and only for a particular choice of helicity. We are not writing down in helicity basis. We'll write down in terms of tensor factors and the form factors, which is not sensitive to particular helicity. It's more general. And if you put particular helicities, it will reduce to this expression. You will see. I will give an example.
Yeah, that's what I wanted to know. Okay.
So, okay. So we define these two dot products, and the reason for defining this is that if in our analysis, this O dot product is very important. Otherwise, we'll get wrong results. So again, the 3-point function of two scalars and one massive spin particle is this thing. This is the polarization of the massive particle, and these are the two massless particles which are scalar, and K12 is basically the difference, K1 minus K2. Okay, so now I will try to write down the 3-point function of photons with a massive spin particle, which, as I said, is known in the literature. It's not our book. So to do that, first I define these two expressions. Only if you are interested in the details, is basically this is the field strength, Maxwell field strength, and out of two Maxwell field strength, I define this object W, which is basically a particular contraction of two Maxwell field strengths of particle A and particle B. Okay, so this I will be using to write down our expression. Then the minimal 3-point function of photons with one spin J particle is this quantity. Okay, this is a very straightforward exercise, and it's known in the literature. Now, I just want you to look at this expression and just note one thing, that this expression, if I define this operator, forget about this normalization. So I first define this derivative operator. then note this expression of the photon spin j 3-point function can just be obtained from the scalar spin j 3-point function through this operator. Okay, so this is our first observation, that the 3-point function in this case I wrote a minimal 3-point function. In general, for other 3-point function, this operator can be written down. I'm just doing it for this particular case. For non-minimal, it becomes even simpler. It becomes a multiplicative operator. And for other 3-point functions, we have given it in our paper. But the observation is that the photon spin j 3-point function can be written as a derivative operator acting on the scalar spin j 3-point. Okay. So with that thing, let's now move on to the 4-point function of the scalars. The 4-point function of the scalars is this expression. So if I take that expression of the propagator, if I contract it with the 3-point function, you get this. And again, this is a known result. And this reduces to famously the 𝗬𝗫𝗶𝗿 polynomial. And again, the normalization is well known. This is the normalization. Again, it's not our work, it's an old result. So now this is our main 2 ingredients that we used, this 4 scalar amplitude and the derivative operator. And what we tried to say in this paper is that let's say now I am interested in 4 photon amplitude. So these are 4 photons due to a massive spin j exchange. Then our claim is that the 4 photon amplitude is simply the action of the derivative operators on the 4 scalar amplitude. Okay. So let me summarize. From the information of the 3-point function, I get the derivative operator. And I claim that in order to get the 4-point function for more general 3-point functions, I just use this derivative operator on the 4 scalar 3-point function. 4 scalar 3-level amplitude due to massive spin exchange. And we will be able to do any spinning legs through this method. Okay. So let me proceed. Is there any question at this point? Okay. So with this, let me give a very simple example. This is the simplest example I can think of. Then let's now consider the yes.
Sorry to
yes, please.
disturb. Just to let you know, you are 20 minutes into the talk.
Okay, thank you. Yeah, yeah. Okay. So so let me now consider the case where we have 2 photons and 2 scalars. So I'm considering this case. Let's say these 2 are photons and these 2 are scalars. Again, 4.4 photon also can be done, and we have done it. But we are considering for simplicity that these 2 are photons and these 2 are scalars. In that case, we use this method. We computed the amplitude, and the amplitude takes the following form. Okay. So as I said, that there are 2 things. One is called the form factor and one is called the tensor factors. Okay. So these are the tensor factors, which is in terms of the W that I written before. And the form factors are explicitly can be computable, and these are these we have written down in terms of the derivatives of the 𝗬𝗫𝗶𝗿 polynomial. Okay. So I just give you one particular example. But in the paper, we did all possible cases with massless particles. I'm sorry, I forgot to mention that we only did the symmetric traceless exchange. We're trying to do the other possible exchanges because we believe it can be extendable. And these are the things we computed. The main goal of the paper was to compute the 4 graviton amplitude. The 4 graviton amplitude seems to have 19 different tensor structures. And the explicit expression, it took us almost 2 pages to write down, so I'm not showing it. And as I mentioned that we did it for the minimal coupling because somehow the 4-point function computation is hardest for the minimal coupling. For non-minimal coupling, it becomes a much simpler computation. And in many cases, and some of the non-minimal couplings are available in the paper written by the TIFR group, and it just becomes a multiplicative operator. It's a simpler multiplication for the scalar amplitude. Okay. So this is our computation, and I will end with some very some more comments. So firstly, this derivative structure is though just a very algebraic tool in case of field theoretic amplitude, but probably this has some meaning in the case of string theory, where we already have a spectrum generating algebra. So a natural question to ask, and this question was posed to us by Ashok Sen, that can we generalize this algebraic structure for string amplitudes? Can I compute any string amplitude in string theory starting from just 4 scalar amplitude? Okay, and on that note, one can ask that does it have anything to do with the higher spin gauge invariance and all sorts of things that, for example, Gross and Mende was talking in the 80s, late 80s. Okay. As I already mentioned that we did this case only for the symmetric traceless exchanges, and it's only a particular subset of the cases. There are more general exchanges and they're important, and they become only relevant in 4+1 and higher. But there is a reason to go to 4+1 and higher, because in 3+1, the scattering amplitude of massless particle is ill-defined due to the presence of infrared divergence. So if we want to, let's say, use some of these techniques to in the case of bootstrap and all this, then I think it's easier probably to go to higher dimension rather than solving the infrared problem in 3+1 dimension. But if we want to go to higher dimension, we have to consider these things into account, and which some of the things we are trying to do. And as many of you know, that in this paper, the authors tried to show that the 4-scalar amplitude is unique, and it's unique in a particular limit, which is an unphysical limit. A simple-minded question one could ask is that, can I do these things now with the 4-graviton amplitude? The main difficulty we're finding is just the mammoth structure of the amplitude. Probably there's a very clever way to handle it. Probably we are not clever enough to do that, but this is one question that one can do. And the more ambitious question could be the following, and it's related to what Pranjal Pandey wrote recently a paper, that in string theory one can ask the question that what is the strength of the 3-point functions? And in string theory, the 3-point function strength is explicitly available thanks to Pranjal. But one could now ask in a bottom-up way, maybe following some strategies that the TIFR group or the Camino et al. Paper followed, that can I now constrain the 3-point functions? Can I say more precise things about the 3-point functions? And can I show that, at least in some sense, the strength of the 3-point function becomes something like the string theory? Okay. So with that set of thoughts, I thank you for your attention.
Thank you, Arnab, for a very nice talk. We have some time for questions. So I see Somdata's hand is up first. So go ahead, please.
So how would you incorporate internal symmetry indices in these cases? Because in general, like the gluon for the gauge boson, you would have internal symmetry indices even for higher spin operators.
I think, honestly, I have not tried to incorporate non-abelian structures into that. Because in general, what happens in non-abelian, you have to, the good thing about this case is that we managed to write it down in a gauge invariant way for every channel. But typically what happens in non-abelian theory is that all the channels are important to ensure unitarity. Okay, and again, I believe there is a paper, I think Abhijit is one of the co-authors, where the gluon 3-point function, gluon with spin j, is known. But we have not tried. I have not tried it, so I don't have much time.
Also,
Sorry, Somdata, I see that there are multiple hands up. So let's move on to the next question by Sachin.
Hi, Arnab. You did it. You are doing in 3+1 dimension and covariantly, right? In momenta.
So Sachinda, we did it in our expressions are available in any dimension, but we could only cross-check with the angular distribution formula only in 3+1.
Yeah. So my question is the following: in 3+1 dimension, it is known that the covariant expression for flat-source amplitude even for 3 dimension, even for 3-point function and the spinor helicity answers, they don't match.
Yes.
For 4-point function also, do you see the same puzzle?
For 4-point function, if I remember, there is a paper by this Nima and other people, this massive spinor helicity paper. Since you pointed out, I will cross-check it again, but when we put it out, we cross-checked with the available result for the helicity expression that those people written down, and I believe we reproduce the same formula.
Okay, so these are generally supposed to match only in light cone coordinates, light cone gauge, etc., etc. Those has been shown, but covariantly it's a puzzle still. But you're saying for 4 point you have checked.
Wait. So if you are saying, so firstly we are doing on-shell, right?
Yeah.
So on-shell expressions, two on-shell expressions can at most differ by a contact term, which is again has been classified the 4-point contact terms. So when I do this expression, we also subtracted off some contact terms because of the expression of the propagators. In some cases, not in all cases. So my claim is the following. I think what we managed to prove is that the expression that the spinor helicity people did and the expression we did, they are same in almost all cases. In some cases, if the external legs, not for massless particles, but if they're massive particles, we also tried with massive particles, then the two expressions differ by some form of a contact terms. That's what we found.
Okay.
Next question by Loga. Loga, go ahead, please.
Yes. Hi, Arnab. Nice talk. So I wanted to just ask one question. You've calculated the graviton force scattering, right? Like you guys claim to have all the structures and so on. So can you actually, I was wondering whether you can structure to see whether is there some kind of a very specific higher spin interaction, which when included, you can kind of absorb this known non-renormalizability in gravity, like the Gourav Banerjee divergence and so on.
Loga, I am not aware of this divergence, so maybe I have to talk to you and then I can.
No, this is a standard divergence that the pure gravity is non-renormalizable.
Yeah, pure gravity is non-renormalizable, but you are meaning the loop computations are non-renormalizable, right?
Yeah, the two loop computation by Gourav and Banerjee and so on.
Yes.
Standard thing. So what happens is that there's a way of thinking about it where you just think about it as like some plus graviton, 2 plus graviton go to 2 plus gravitons. You can just look at that scattering and you can kind of understand the divergence showing up there.
So I think what you are trying to say, in order to understand that, I also need to understand the loops of the massive particles, because otherwise the analytic structure of the loop here is a pole, so it's not a local term, whereas your non-renormalizable terms are not local. So I think don't you think we have to look for loops, and we did not look at that very carefully.
Yeah, so maybe let me just say, so if the higher spin particle is very massive, you would think that this exchange diagram will become like a contact diagram.
Okay. Yeah, I think in that limit, we did not look at it, but I think it is possible to back calculate that what we could do to remove that divergences.
Yeah. So the question is
sorry. Yes, go ahead.
Can you say what higher spin spectrum? Let's say I say that there's a particular contact term which is generated by some massive higher spin which is absorbing this divergence. Can you say something about the spectrum of higher spins that are needed or things like that?
Yeah, thank you, Loga. We have not explored, but I think in that limit it's possible to understand that question. Yes.
Okay, Alok.
Hi, Arnab. Yeah, so just a small question related to your discussion with Sachin. So, in the spinor helicity basis, the 3-point coupling of 2 massless and 1 massive for any spin of the massive and any helicity of massless is unique. So why?
Yes, correct.
So why would we not use that? Sorry, I was a bit confused, but wouldn't it be easy to use that 3-point coupling and to compute these 3-level amplitudes, or we missed something?
So if I understand correctly, that the result that available in the more general covariant way in all possible dimensions, if you take that result and if you go to 3+1, and
I meant in 4 dimensions. Yeah.
In the helicity basis, then it reproduces the massive spinor helicity results. Only advantage of using the result of the TIFR group is that their expressions in more covariant is not helicity dependent, and it's useful for our way of doing things. But if you actually try to take them and write in helicity basis, it agrees with the result of the spinor helicity.
So in higher dimension, the coupling is not unique. You're saying, like in 4 dimension, is that one? Is that?
No, I think even in that case, it depends. In the helicity basis, I believe it's possible to show that it's again unique. Because the number of structures...
We may not have spinor helicity in arbitrary dimensions, so that's why I was asking.
Correct.
Yeah.
Again, you can write down a massive particle in, let's say, d dimension as a helicity basis, and you can write down the helicity amplitudes, right? Not in spinor helicity, but you can write down helicity amplitude.
Right.
I have not tried, but what we played with this, it felt like that this particular case is still unique.
Okay.
And it's not, I only played with the result that's available from the TIFR.
Thank you.
Akshay.
Hi,
Akshay, please.
thanks for a great talk. Actually, my question was also about the contact terms. Is it, if I understand correctly, your formalism only captures the exchange interaction and not the contact terms?
Correct.
Is it possible to fix them in some way by either demanding like perturbative unitarity or something like that?
I have not thought, but there's a complete classification already of the 4-point contact terms, right?
Oh, in any dimension?
Yeah, I think, I mean, Abhijit can tell better. Yeah, I think, I think that, it's a complete classification of the 4 graviton contact term available. So the only problem then remains is to just determine the coefficient.
Okay. And is there a way of doing that?
So it depends. See, the propagated expression that is available in the literature for spin J, the theta I showed you, if you remember, eta mu nu over p mu p. There are actually 2 expressions. One people uses 1 over p square, one people uses 1 over m square. So again, depending on that expression, the contact term changes. The only thing that remains invariant is the pole term. So I think in one particular scheme of things, if you use our particular propagator, then yes, it's possible to determine the numbers.
Okay. Thank you.
Thank you.
Sandeepan?
Hi, Arnab. Nice talk.
Hi. Thank you.
I have one question and one comment. The question is actually, it looks like from your results and from your setup, it looks like the impact parameter space might be the right language to talk about this kind of amplitudes, because like from Kaim's paper, we know that in the impact parameter space, actually all the 4-point amplitudes, at least for at the tree level, they factorize us.
Right, I agree. Yes.
So, and is that correct? Like that's the right. Like
I agree with your observation. The reason we did not still write the reason to go for me to impact parameter will be to also to understand some more properties, like something from the bound, something from causality. And if I understand correctly, the 4-dimension impact parameter expression is logarithmic divergence. So I cannot trust the tree level result. So I was more interested into going to higher dimension, but then I need to understand more contributions to the 4 graviton amplitude.
Even it will be a log of like B is the impact parameter, but like since you'll have all the derivatives acting on it, like it will be completely fine. So that's just an observation. The comment is actually like there are some theorems about massive high spin particles that are known. Probably they are your.
I think few of them you and some other people wrote down. Right?
It looks like your results should be useful in that context. That's just a comment.
Maybe I should contact you, because we tried to look at that, and we tried for a bit of moment, but I looked at that, but I don't have any. It also looked to me that we can prove those results, but. Maybe I misunderstood some part, so maybe
we could talk separately. Yeah, that's fine.
Okay,
thanks for the talk.
Okay. Thank you.
Great. Thanks again, Arnab, for a very nice talk, and also let me thank the other 2 speakers of the morning session, Akshay and Koushik. So with this, let me hand it over to Alok.
Thanks, Abhijit. So let's reconvene in 15 minutes, roughly 11:45, please. 11:45. Thank you.